Good afternoon, ladies and gentlemen. So I'm Peter Haynes, the head of DAMTP, Department of Applied Mathematics and Theoretical Physics, and I'd like to welcome you to the fourth Andrew Chamblin Memorial Lecture. The first three lectures were given respectively by Stephen Hawking, Roger Penrose and Paul Davis, and we're very pleased that today we have Professor Michel from the University of Geneva as our fourth lecturer. I'm going to ask my colleague John Papaloizou in a minute to introduce Michel Mayor, but first I'd just like to say one or two words about Andrew Chamblin and about the establishment of this lecture series. So this is a picture of Andrew Chamblin. Andrew was born in Lubbock, Texas, and he attended Rice University before coming here to the UK, spending a year at Christ Church with Roger Penrose, and then moving to Cambridge as a PhD student. And in Cambridge he worked under the joint supervision of my colleagues Gary Gibbons and Stephen Hawking, who both feature in this picture, with Andrew as the person in the rear on the left. So over his career, Andrew's interest turned from twistors, classical relativity to quantum gravity, and then to M theory. And over his career, he made a number of striking contributions to research, published over 50 papers, and he delivered many talks and lectures around the world. After he completed his PhD in DAMT, Andrew became a Draper's Research Fellow at Pembroke, and then he moved on to other posts and fellowships before being appointed to an assistant professorship at the University of Louisville in Kentucky. And it was there that he sadly and unexpectedly died on 6th of February 2006, at the age of 36. So Andrew's many friends and collaborators in DAMT and elsewhere have established a fund to support a series of lectures to perpetuate his memory and also to promote the broader area of science in which he was interested. And in fact, there is now sufficient money in the fund that we can hold these lectures in perpetuity. And we in DAMT are very pleased to have the responsibility of organising this, and we're very pleased to add it to our list of important annual lectures. And it's a particular pleasure to welcome here today many of you who've helped in establishing the fund and given to it. In particular, I'd like to welcome Andrew's mother. We're very pleased to see you here today. And in fact, Andrew's parents have also donated to us in DAMT a striking bust of Andrew, which is a nice addition to our departmental furniture, so to speak. So this lecture each year is a chance to remember Andrew as a theoretical physicist, as a colleague and as a friend. So now I'd like to move on to today's lecturer, and I'm going to hand over to John Papaloizou to introduce Michel Mayor.
It's my great pleasure to introduce Professor Michel Mayor, who is an astronomer based at the University of Geneva. He is well known for his leadership of the Geneva extrasolar planet search programs that have led to this discovery of so many extrasolar planets. Professor Mayor studied physics at Lausanne University and obtained his PhD at the Geneva University in 1971. He then became a research associate at the Geneva University, eventually becoming Professor of Astronomy in 1988. His early work was concerned with the development of spectrographs for the measurement of stellar radial velocities, which, with improvements in technology, eventually led to the detection of low-mass companions orbiting Sun-like stars. Thus, together with Didier Queloz in 1995, he discovered 51 Pegasi b, the first extrasolar planet orbiting a Sun-like star, 51 Pegasi. Since then, Michel and his research team have been mainly occupied with the discovery of many additional extrasolar planets, there being about 450 to date. This confirms that the Sun is not unique among stars and hosting planets, and it expands the search for possible extraterrestrial life beyond our solar system. In 2003, his planet-searching instrument, the high-accuracy radio velocity planet searcher, came online, and in 2007 he was one of 11 European scientists who discovered Gliese 581d, which is the first extrasolar planet believed to be in a star's habitable zone. That's where you might think the conditions are favourable for the existence of life. And this was done from the European Southern Observatory's telescope in La Silla, Chile. More recently, in 2009, Michel and his team discovered the lightest exoplanet detected around a main sequence star, Gliese 581d, which is only twice the mass of the Earth, but with a very much shorter orbital period of only 3 days. Well, the significance of Michel's many contributions has been recognised through many prestigious awards. In August 1998, he was awarded the Swiss Marcel Benowitz Prize in recognition of his work and its significance for human life. In 2000, he was awarded the Balzan Prize. In 2004, he was awarded the Albert Einstein Medal. And in 2005, he was awarded the Shaw Prize in Astronomy. This year, he was made a Foreign Associate of the US National Academy of Sciences. Well, Michel's title today will be The Amazing Diversity of Planetary Systems. So please join me in welcoming Michel Mayor as the 4th Andrew Chamblin Memorial Lecturer.
Thank you, John. It's a great pleasure to be here. And I would first give my message to the family of Andrew Chamblin and his friend and all ladies and gentlemen in that room. I'm proud to be the first to have the privilege to give a lecture not on cosmology in this series of lecture. And evidently my talk will be devoted to the description of the incredibly lot of research we have acquired on the last 15 years in the field of extrasolar planet. And the main point I would like to show is the huge diversity of planetary systems we have in the universe. And this is a rich source of inspiration to understand the mechanism of formation of planets. Everybody of you know the Sun is only one star in a very big family, the Milky Way, located in some place in the external part of such a system. Evidently, this is not the Milky Way, but is a similar galaxy. And we have something like a few 100 billion of stars, similar to the Sun in some sense, in such a system. And evidently, we would like to know if we have planets. Later on, I will put some discussion on this small pink dot we have here. It's the place of formation of new stars. If we look at a small place in such a system, you see that we have plenty of stars. The problem is not to discover new stars. We have as much as we want, as many as we want. You see every point here are something similar to our own solar system. But evidently, we don't know how many planets we have here. And this question is very strange. If we are looking back in the past, during the 20th century, the ideas on the subject have drastically changed in the 40s. Maybe some people from Cambridge can recognize some names, not be working too far from here. And you see that at the beginning of the 20th century, until the mid-40s, the general understanding was that the planetary system was extremely rare in the galaxy, in the Milky Way, maybe nothing except the solar system, or maybe a few. Here is the logarithmic scale. And suddenly the paradigm changed completely in the late 40s, in the mid-40s, jumping to 2 billion to 100 billion of possible planetary systems in the galaxy. So in fact, it's the idea that we should have a lot of planetary systems is relatively recent in the community of astrophysicists. I have also to put some credits to Victor Samofronov, only 40 years ago, giving the first route, first path to understand the formation of planetary system by agglomeration of planetesimal, starting from dust grain, ice grains, in an accretion disk. An accretion disk is some kind of disk of matter relatively fastly rotating around the young stars. So in some sense, at the end we will see that planet is some kind of byproduct of the formation of stars themselves. And I believe this is a very key observation. Everybody was sure that accretion disk exists around young stars, but this was directly seen also 15 years ago, that this is the Orion Nebula. It's you see this relatively close by molecular clouds where you have a new generation of stars, and the Hubble Space Telescope took some images of young stars in front of the nebulae. And you can see in negative, because dust is stopping the light coming from the nebula, this accretion disk, this disk of matter, fastly rotating around the young stars. So in fact, I believe that about 70% of the young stars have been discovered to have this kind of accretion disk. But probably maybe we have more, but simply the sensitivity of the instrument was not enough. So a priori, we can believe that almost 100%, the huge majority of stars should have planetary system, because we don't have reason to believe that the agglomeration of dust particle is working here and not here or not here. So a priori, we are quite confident we should have a lot of planet. This is a very normal process in the universe. Evidently, it was quite difficult to discuss this. People were starting already in the 50s in the US, Peter van der Kamp and others, to try to find planet, but it was quite difficult because the reflected light by a planet of the light of the star is so small that we have no chance, at least at the time, to directly see the planet itself. And it's only from the 80s, 90s that different teams start to try to detect indirectly the planet by just the reflex motion. If you have a star here, you have an orbiting planet here, eventually you have a small motion of the star itself due to the gravitational influence of the planet. And eventually, due to the mass ratio between both, it's the reflex motion of the star is very, very teeny. And it's not so evident to see the change of the velocity. And we have built with our French colleague a new instrument implemented on a very relatively old telescope, 2-meter class telescope. This telescope is not so important. What is important is the sensitivity of the spectrograph. And soon after having finished the construction of this instrument, we measure a sample of something like 140 stars similar to the sun. And we discovered quite soon the change of the velocity versus time. You have the velocity here versus time of the star. This star was called 51 Pegasi. And you see that the periodic change of the velocity, it was exactly what we are looking for. And this is a signature of something disturbing the velocity of the star. And it's very easy to estimate what is the period, the mass, and shape of the orbit of this object. And what was the surprise? That this corresponds to something like half the mass of Jupiter, but with orbiting period as short as 4 days, 4.2 days. And it's evident we do not have in the solar system any big planet like Jupiter with a period as short as 4 days. And the theory was not expecting to have such kind of object at that time, because to build such a relatively massive object, you need to agglomerate a lot of dust and ice particles. And close to the star, you don't have ice particle, you don't have enough dust particle, so it's not possible to build directly such a massive planet here. And so the theory was predicting that massive planet, a Jupiter-type planet, could be formed only in a period of 10 years and more, like we have in the solar system. So how to understand the change of period or the formation mechanism for such an object? And I believe, okay, apart the philosophical satisfaction to have discovered a planet, I believe this was the most important point. We have something missing in the theory of planetary formation. In fact, it was not true that it was not completely true that this piece was missing, because already 15 years before, in 1980, you have in the literature a paper by Peter Goldreich and Scott Tremen. And you can see in the abstract of this paper, because they studied the influence of a body embedded in a disk. It could be a small galaxy embedded in a disk of galaxy. It could be a planet embedded in an accretion disk. Something similar in both situations. And at the end of the abstract, you see, we present an illustrative application of our result to the interaction between Jupiter and the protoplanetary disk. The angular momentum transfer is shown to be so rapid that substantial change in both the structure of the disk and the orbit of Jupiter must have taken place in a time scale of a few thousand years. So you see that already the mechanism was already present, but you have so many papers, we don't read carefully everything. So nobody changed to discover this kind of short period planet, because before we have discovered 51 Pec. So I will not describe too much, just a few ideas. So this was deeply studied by many people later on. And the idea, this is evidently a simulation, it's not a picture. Here you have a disk of dust and particles. You have a young planet formed here in the simulation. This planet will take the matter in the corridor, in the gap here, and evidently later on, the mass of the planet will induce some density wave in the disk, excess of dust and particle here. And thus this excess will react on the orbit of the planet itself, and the net result in that case will be a shrinking of the orbit. So you have the basic mechanism to explain, to understand the spiraling, the migration of the planet towards the star. And this is very a crucial phenomenon. The detail is extremely complicated. And for example, why the planet will stop and not be engulfed in the star itself, and so on. You have a lot of complexity, but the basic idea is that one. And evidently, this is a key factor to understand the diversity of planetary systems. In fact, today, people start to have the capability to do images of accretion disks. And here you have few examples of disks where you can see the structure of some kind of structure. It's not a smooth density of this kind of accretion. And we can expect in the close future to have the capability to have much better detection of the structure of this kind of accretion disk. As you know, that combined effort of Europe, US, Japan is going on the north of Chile to build an interferometer of something like 50 antenna at 5,000 meters to have the possibility to study cold gases in the universe. And evidently, you can do formation of galaxies, formation of stars, you can do, but eventually you will have also the possibility to study protoplanetary disks. So this is not a long-term project. It will be coming in only a few years from here. So if now we go back to what we have discovered in this huge sample of more than 400 new planets. In fact, here is a very sketchy diagram of what happened in the last 15 years. During the first 10 years, mostly we have, when I say we, it's all teams working in the domain, have discovered objects in the domain of gaseous giant planets like Jupiter or Saturn. Right now, we have the capability to detect Neptune-type planet and super-Earth. What is a super-Earth? It's not a kind of planet we have in the solar system. It's a term to denominate object with a mass between 1 and 10 times the mass of the Earth. We don't have any planet similar to this kind of object in the solar system. Neptune is something like 17 times the mass of the Earth. And the future, evidently, is to see if we have a chance to detect objects like that. I will not give too many value estimation data, but just to keep in mind that the Earth is 300,000 times smaller than, less massive than the Sun. So it's about a little bit more than 1/1,000,000th of the mass of the Sun. It's a very smaller body compared to the mass of the Sun. Just another look. This is an historical diagram where you have the mass of the object detected as a function of the years. Here you have, it's a logarithmic scale, so you have the Earth, Neptune, Saturn, Jupiter, and so on. And these are all the low mass companion to solar type stars. Evidently, you have the object orbiting pulsar discovered by Alex Volkshan in 1992 here, but is maybe a very special case. And then these are object orbiting solar type stars. And okay, you can see the dramatic, this is 51, but you have the dramatic increase of the discovery from that time. But the second important point is the fact that you see that the sensitivity of the instrument increased by a huge factor during the 15 years. You have a factor 1,000 from here to here. It's a huge improvement, evidently, the capability to detect a lot of interesting objects. Problems. So, this is the material from which we have acquired a lot of information. And now if we enter the problem of the diversity, it's a diversity on all the aspects of planetary system. Distribution of period, distribution of orbital eccentricity, the shape of the period. The fact that we have a lot of multiplanetary system, but with specific characteristics. The mass distribution, the metallicity, we have a lot of information relating the metallicity of stars versus the frequency of giant planets. It's evident, if you do not have enough dust particle to start the process of formation of planet or ice particle, it's more difficult to form a planet. So it's evident we should have something similar to here. So I will try to go through this observation relatively quickly. Eccentricities. You know that in the solar system, the 4 large planets in the system, Jupiter, Neptune, Uranus, and Neptune, are almost with a circular orbit. It's almost circular. If we are looking at the orbits of extrasolar planets we have discovered, you have eccentricity versus logarithmic of the period here. If you have 0, it's a circular orbit. If you are here, you have extremely elongated orbit. So you can see the first look you can have that most of planetary systems have extremely eccentric orbit. Here you have Jupiter, it should be some place here. So you see, and evidently Saturn is out of the diagram here because it's too long period. You have a lot of possibility to explain the pumping of the eccentricity. You have maybe too many possibilities to affect the eccentricity of planet. But you see this, and you see that some characteristics have used different symbols in this diagram. And for example, you see the most extreme eccentricity are observed for planets belonging to binary stars. When you have 2 stars and you have 1 planet orbiting one of these 2 stars, in fact, in some case, you can have extreme eccentricity in such case. And you see that we have seen the drastic influence of the migration in the disk at the time of when the star is young. But you see that dynamics is probably a key ingredient to understand the diversity of planetary system. Just an example, here is always the velocity versus time. As it is a binary stars, you have a drift due to the hexagonally, and then after you have this very strange curve, a Keplerian curve. Here this is a curve alone, here, and this is the signature of a very eccentric orbit. So it's something like this. Another characteristic we have in this kind of system is related to some kind of resonance, again, dynamics. Here you have a system discovered many years ago where you have two giant planets, one with a 1 month period, the other one with 2 months period. It's almost exactly a factor 2 between both of them. So one planet is doing 1 turn, the other one is doing two orbits, two period, two rotation. And here recently we have discovered a system with a ratio 3:2. Here there's a system with 3:1 and so on. And this cannot probably be understood without also the influence of migration to lock the two planets in the system with a resonance. Again, influence of migration. And soon after the discovery of the first planet, people realized that if you have so many cases where you have a very close planetary system with a short period, you have a good chance to have the possibility to have eclipse. So if the orbital plane is good enough to have just the possibility to have the planet going in front of the disk of the star, you can expect to have a small periodic drop of the luminosity. We prefer to use in this case the case of transit, but it's something similar to an eclipse. And this opens a completely new field of planetology because we can have access to some physical characteristic of planet. This was the first object. We start with the discovery, always the same kind of diagram, velocity versus time. It's a period of 3.5 days, something similar to Jupiter. And we can expect that if the orbital plane is correct, that we can have some transit here, at that time here. And exactly at the good time, in September 99, we can see, we have observed, in fact, not here, we have some colleagues, because we gave the ephemeris to some colleagues in the state at Boulder, and they have observed this small drop of the luminosity by a little bit more than 1%. And it's so easy to understand what you can do from that. Because we have the star, and you have the planet. And the drop is directly a measure of the relative size between the planet and the star. So if you know by the theory what is the size of the star, you can derive an estimation of the size of the planet. And if you have from the velocities, you have the mass, the radius from the drop of the dip of the luminosity. Combining these two quantities is evidently easy to have the mean density. And the mean density corresponds to 0.3 gram per cubic centimeter, is less than the density of Saturn. So it's a direct proof that we have gaseous giant planet. So this was very important because still at the time some colleagues was not believing it was planet. The next season, our colleagues from US ask again time to remeasure the transit of the same star, but with a space telescope. And evidently you have a big advantage because you are out of the atmosphere. And if you are out of the Earth's atmosphere, evidently the quality of the photomagnetic measurement is drastically better. And here this is the original ground-based measurement. The scale is different, but it's exactly the same phenomena. It's about a little bit more than 1%. And you see the quality of the data you can obtain in the space with an instrument not done for that. Hubble space was never designed to do this kind of precise measurement. So immediately you can dream that you can do something better with a dedicated instrument. And this was a source of the idea to build a specific instrument in the space. One is sent by the French, and ESA, it's called CORO, it's a very small telescope. And now last year, NASA sent this new mission, Kepler, with a much more ambitious telescope with 90 centimeters here. And you see this original measurement of that star. And you see if Jupiter will have would create some kind of as deep as 1%. Neptune will create something like this, and the Earth will create something like 100 times smaller than Jupiter. So you see how it will be difficult to detect the crossing of the disk of a star by a telluric planet, a terrestrial type planet. It's so small deep. And let's imagine you have 10⁻⁴ deep, but only once every year. And as you know, every star are variable. So this is a challenge to detect a terrestrial or rocky planet. The very small Corot telescope last year discovered not a terrestrial planet, but something similar. It's a little bit larger, it's 1.7 times the radius of the Earth, and this corresponds to about 3 times the deep expected from a terrestrial planet. So you see it's 3 times 10⁻⁴. Evidently, they have a relatively big advantage because the period was only 0.8 days, 20 hours. So evidently, still more extreme than 51 pig. So what we can do with this kind of information? Planetary internal composition. We can have some insight in the internal structure of planets. Here, this is diagram done by people understanding the geophysics, or I don't know if geo is correct, but physics of planets. And here you have the radius of the planet with unit of 10 to the 4 kilometers. And here you have the logarithmic scale of the mass. And if you know enough of the theory of the matter, you can build in the computer the relationship between the radius and the size. And if it's a pure iron, you have something similar to that. If it's only rocks, it should be something like this. Pure ice, it should be something like this. And pure hydrogen and helium, it should be something like this. So then after you have transit, and you have the determination of this is the first transit here. And you can see that you have quite a lot of possibility to analyze the relationship between the size and the mass of planet. And the first strange observation was the fact that Jupiter-type planets don't have the same size and the same density. You have a huge scatter of the density. In fact, the transiting planets most of the time are inflated. And it's not so easy to understand this because if you have pure hydrogen and helium, how you can have still larger planet than this? If you have a lot of heavy material inside, it's easy to be below, but to be above is not so easy. So you need to have some source of energy to inflate this object. So this is still not a completely solved problem. A lot of people try to understand this point. Here you have Neptune and Uranus, some kind of icy planet. And this was an exoplanet discovered 2 or 3 years ago. So we start to have the capability to analyze this relatively low mass object. And Corot discovered Corot 7b. It's the name of one of these objects. And the location of this object should be close to here. So I don't know if it's exactly pure rock. Okay, the error bar is still not negligible. But you see that we start to have the possibility to analyze the object close to the terrestrial planet. Just to have an intuitive view of the difficulty to do this kind of measurement. Here you have, it's a real picture of the transit of Venus done in 8th of June 2004. This is a disk of the sun. You have some kind of spots here, but this is not a spot of the sun, but this is the size of Venus. So what you expect to do to measure extrasolar planet, rocky planet, is to see the drop of the luminosity of the star when you have something similar to this crossing the disk. And this gives the difficulty of this object, of this kind of measurement. Now, you have seen that you have the very small telescope called CORO. Then after you have the big telescope called Kepler. Both have some advantage but have some difficulty. And today, ESA is designing a new kind of instrument to search and to study transiting, not focused on a small region as Kepler or CORO, but to have a very broad survey of the sky, but to measure only bright objects. Why it's more interesting? Because if you have to find objects, what we can expect from this first mission, it's extremely difficult to measure the velocity of this object to acquire more additional information. So just to have an idea what you can do when you have bright stars. This is CORO 7b, 153 transits. It was extremely difficult to get the 3.5 or 10⁻⁴ of the contrast of this periodic dip. But you need, with the expectation with Plateau mission, will be only after 3 transits we will have the capability to detect really a rocky Earth-type planet. So I believe this will be an extremely interesting mission if this mission is decided by ESA. It is still not the case. It's still a project. Just to see the challenge of this kind of measurement. Here, this is the same diagram as we showed before. It's the radius versus mass with a different curve you can have with different kind of composition. If it's a Mercury-type planet, it will be something like this with a big core of metals. This is pure iron here, and so on. And you see the typical error bar we have today is the black line here. Maybe you can have something better for some extreme cases, a little bit better. And the Plateau experiment should provide an error bar as small as this. And this is critical if really we would like to have the possibility to distinguish the internal structure of the composition of this kind of objects. Why it is interesting? Because this is an additional kind of constraint of the theory of the formation of planetary system. Some people, you have different groups in the world, are trying to put the physics of the formation of agglomeration to form planet and to some kind of Monte Carlo population synthesis. And here you have the mass predicted versus the semi-major axis. So the Earth will be here, 1 Earth mass, 1 AU here. And then after they run the computer and to see just what kind of planet you can form and what kind of density, what kind of frequency you can have in this. And what is the result is something like this. You have 2 key events in this diagram. One is a migration. You can see that the semi-major axis is shifting to the right towards a smaller, shorter period. And in parallel, you have the increase of the mass due to the accretion of matter. So, and evidently, you see that the final result is directly related to the initial condition where you start. If you start to migrate from very far outside the disk, where you have mostly ice particle, evidently you are not finishing with the same composition if you are starting directly in the inner region of the system. So just to see that the composition is not different, it's piece of the same processes, the same scenario. I'm obliged to skip all the things related to the spectroscopy, but it's evident we can have also some information on atmospheric parameters. But I will just give you a more technical but new result. I just repeat that we still not have seen one of these planets. It's only indirect detection. And this is a beautiful, I would say, kind of observation showing the possibility to have still a more apparently difficult parameter of this planetary system. In fact, when you have the star here rotating like this, we expect from the migration that the orbit of the planetary system will be almost in the equatorial plane of the star. So I will show that it's possible to measure the relative angle between the equatorial plane of the star and the inclination of the planet. In the solar system, you know that the sun is a little bit tilted versus the ecliptic. How can we have access to this kind of parameter? The name of this phenomena is called the Rossiter-McLaughlin effect, discovered in 1924 for binary stars. Let's imagine this is a star. It's a rotating star, so rotating with an orbital axis like this. So the star is rotating in that sense. And in addition, you have a planet crossing the disk. Evidently, when the planet is here, we are stopping the light from one part of the star moving in your direction. And at the opposite, when this planet is here, you are stopping the light of a part of the star going opposite to you. So you will affect a little bit the mean velocity you are measuring with the spectrograph. You see that you are deforming the shape of the line due to this effect. And so the transit of a rotating star creates a distortion of stellar line and an anomaly of the velocity curve. So if the planet is crossing exactly perpendicular to the orbital, to the spin axis of the star, you expect an anomaly, something similar like this. The shape gives you the information if the rotation is the same sense as the spin of the star, and if it's perpendicular to the spin of the star. And this is typically the case we have here, with completely symmetric. It's rotating in the same sense of the star, and something like this. If you have a situation like this with an angle between the equatorial and orbital plane, you see that you have a small path on this hemisphere, as half hemisphere of the star, and a big part on the other side here. So you have a disymmetric curve. And in some extreme case like this, you have a curve like this. So if you analyze this kind of curve, you have access to the relative angle between the spin of the star and orbital axis. So this is a quite new possibility. And here are real observations. This is the brightest of the transiting stars we know. And this is, you see, this is the radial velocity curve due to the orbits of the planet around the star. This is Kepler motion. And here you have this small Rossiter-McLaughlin anomaly. And this is a perfect example of a planet crossing perpendicularly to the spin of the star, and in the same sense of the rotation of the star. So this is the typical example we are expecting from the migration. But recently, people start to discover quite different objects. And for example, here, what you can say immediately when you see that the first lobe is on the wrong side. And in addition, so this is a retrograde orbit, and then it's completely dissymmetric. So you have an angle. So just looking at this kind of diagram, you can see that you have a very strange situation, absolutely not predicted by migration. And here, this is another example published recently. It's evidently an artistic view. It's not a real picture. And you see that here you have the star with rotating around this axis, and you have an orbit of the planet on the opposite side, a retrograde orbit, and inclined. And so immediately you see that orbital migration, we have mentioned before, is certainly not the only explanation to understand the formation of these hot repeaters. So evidently it would be much easier to have direct images of planet. But I will just give some hints of the difficulty of this point. People doing the formation and starting to build real planet and to understand the luminosity as function of time can build this kind of diagram. Here you have the luminosity, a very big logarithmic scale here, versus the luminosity of the planet as function of the luminosity of the star. So if you would have, here you will have a planet at the same luminosity of the star, if it's 10 minus 3, 10 minus 4, 10 minus 6, and so on, 10 minus 9. 10 minus 9 is this very small quantity. It's only 1 billionth of the luminosity of the star. It's the case of Jupiter in the solar system. It's reflected only 1 billionth of the luminosity of the sun. And here, look at, for example, this curve here. This is the expected luminosity of a Jovian planet, a Jupiter-type planet. At the beginning, the luminosity of this kind of planet is still relatively bright. It's about 10 minus 5 times fainter than the star. But then after, this planet will cool down, and when the age is few billion years, it's one part in 1 billion, so it's very fine compared to the luminosity of the sun. So you see, it's much easier to detect a planet when the age of the system is young. It's quite young, let's say less than 10 million years here. So currently, adaptive optics survey have the capability to do images of planets in that domain here. But in the future, what is called extreme adaptive optics is a system having the capability to correct the atmospheric turbulence could provide detection of planets in that domain here. And here, these are the first measurement of something similar to planet. I don't know if it's real planet done by agglomeration, because they are still a little bit massive. They have some problem. But nevertheless, all these objects are few times the mass of Jupiter. And you see you have this kind of very small dot compared to the luminosity. You have some trick to stop the light of the star and so on. These are the very first measurement, but it's evidently far, far, far to be rocky planets. A very nice detection done last year, I believe, by Paul Callas. You have a young star with still some matter around the star, and they have been extremely careful analyzing and detecting a small dots orbiting here. This is an enlargement here. And 2004, 2006, we can just see the orbital motion of the object, but it's massive. It's several times the mass of Jupiter. We are on the good way. And evidently, the challenge is so exciting that many places people are building new kind of extreme adaptive optics system. And here is a diagram where you have the contrast ratio between the star and the planet. Because really, what is difficult is not really to detect the luminosity of the planet, but not to be completely dominated by the light of the star itself. So this is really the difficulty, is to stop the luminosity of the star. And you see, I will concentrate. OK, here you have some prediction. It's different domain of wavelengths, H-band, K-band, 5-micron band here. And here you have different ages and masses. So let's imagine a one Jupiter type. After 100 million years, the contrast will be here, 10 minus 7, something like this. In a different 2 micron, it will be something 10 minus 8, and so on. So you see this already, the contrast is dramatically difficult. And now ESO is building a new instrument to be implemented at Paranal Observatory, but you see it will be implemented on an 8-meter class telescope, but it will only have the capability to detect Jovian planet. It will not go to, we cannot dream to detect telluric planet in the next few years. It's still out of the technical capability. Evidently, it's a different tool. expected to be used by astronomers in this kind of imagery. It's James, I don't know. It's the successor of Hubble telescope, James Webb Space Telescope. You see the 6.5 meter class telescope here. It's very funny shape and so on. Evidently, in the space is easier than on the ground. Another tool could be the new ESO telescope, of 42 meter class telescope with a segmented dish here. And so evidently, if the adaptive optics is correctly done, maybe we can have a point function enough to see very interesting low mass object. Just to have to relax after all this diagram, to have a more relaxing picture. This 42 meter class telescope has been decided on the last last month to be implemented here. It's on the top of Cerro Armazones. It's 2,600 meters, something like this. And this picture is seen from the existing Cerro Paranal, where you have the 4 big telescope or 8 meter class telescope. It's quite dry. Do we have the capability, nevertheless, to detect terrestrial planets in the habitable zone? I believe yes. Going back to this kind of Monte Carlo simulation, here's the same diagram you have seen before, where you have the mass versus the semi-major axis produced with the, I don't know it's correct, but it's what we can do in the theory for the formation of planets. And you see that Jupiter will be something like this here. So you see that already the theory is expecting to produce some more massive planets than Jupiter. So all above this line is gas giant planet. This is typically the domain of icy planet. But you see the huge density expected from the theory for the formation of rocky planets. So small mass planet, Earth mass planet, a little bit more, super Earth or something, all between 1 and 10 is super Earth. This domain is expected to produce a lot of rocky planets. So in the region where of habitable zone, we can expect to find a lot of planets, much more frequent compared to the gas giant planet. So it's very stimulating that we have to do some effort to find this kind of objects. A few years ago, 6 years ago exactly, we have built a new instrument implemented to the Swimprint 6 meter class telescope at La Silla Observatory in Chile. It's a vacuum spectrograph with a huge sensitivity and stability. And with the instrument, we have detected quite a lot of low mass objects. Here in this diagram, you have the mass expressed in mass of Jupiter, so Jupiter will be here, and versus the semi-major axis. So all these symbols are used to show the position of detected planet. In green is by the Doppler techniques, and this kind of symbol are used for the ARPS detection. So you see, with this new instrument, we have detected quite a lot of low mass, a new population of low mass objects. And this one is less than twice the mass of the Earth. It's okay. We have done a very nice job here. But you see, we still have a lot to do if we would like, because the Earth-type planet in the habitable zone is in that box here, in this region here. So we still have to do a huge progress in the sensitivity of Doppler techniques if we want to detect objects in that region here. These symbols are used for microlensing detection, very interesting in terms of statistics, but evidently you cannot do any subsequent observation because it's a single observation. Just to have one example of this huge population of low mass objects is a system detected last year with 3 planets orbiting the same solar type stars with a relatively short period. It's not habitable zone. It's 4 days, 9 days, 20 days, but all in the range of what they call super Earth, 4 to 10 times the mass of the Earth. So this is, you have quite a huge number of similar systems around solar-type stars. And we don't have something similar in the solar system. It's another aspect of the diversity of planetary system. So let's imagine you improve your spectrograph by, I believe we can do a lot of progress of instrumentation. The real difficulty is not the instrumentation. The difficulty is stars are not perfect. You see, this is an image of the sun, and when we say we are measuring the velocity of a star, what is the meaning of this sentence? We are measuring the mean velocity of the atom in the hemisphere in direction of the sun, of your telescope. And eventually you can see that you have a lot of defects. You have the convective zone with matter going up to 1,000 meters per second, going down to the same velocity. You have magnetic field, you have all these problems. And due to the fact that the star is rotating, you have a periodic variability of the velocity. And this effect is much larger than what we would like to detect. Nevertheless, if you select carefully relatively old stars, non-active, and you adopt a strategy of measurement where you repeat the measurement to try to diminish the influence of this, all this magnetic activity and so on. And this has been done by a young PhD student. And in fact, for a period of 200 days, if you have a super-Earth of twice the mass of the Earth, and then in fact you can, this is simulation of measurements on the few years, you see what you are expecting to detect with the existing spectrograph we have today. And if you build the phase diagram of this velocity, we should expect after 4 years or something like this, something like here. And this corresponds to only 2.5 times the mass of the Earth with a period of 200 days. 200 days is a place where you can expect the habitable zone of K stars. It's a star with 0.7, 0.8 times the mass of the Earth. So today we already have the capability to detect planets in the habitable zone orbiting something similar to the sun. So here is a very, very classical diagram where you have the prediction where is called the liquid water zone. If you have the mass, logarithmic scale, versus the distance between the planet and the star, the Earth is 1 solar masses, 1 AU. Here you have the solar system object, Mercury, Venus, the Earth, Mars, and Jupiter. And we are glad to see that the Earth is located in a region where you can have some liquid water on the surface. This is Gliese 581, where you can see such an object close to the habitable zone. But I would call your attention that I'm not expecting that we really have life here because it's a low mass star. It's about 0.3 times. So if you have 0.3 times the mass of the sun, I don't believe that we have so large quantity of silicates to form a rocky planet of 7 times the mass of the Earth. So it's probably a mini icy planet or mini Neptune. And so maybe it's not good for your vacation. So okay. But you know, we are not too far to have the capability. But just with the previous simulation, with a 2.5 Earth mass at around 0.7 times the mass of the Earth, you should be something like this. So, in fact, we have the capability to detect this object. Again, the same diagram we have seen at the beginning. So, the progress of instrumentation. These are Earth measurements. So, we can extrapolate, and soon we should detect Earth-type planet. So, what is the goal? The goal of this kind of effort is first we do not, still today, we do not know how many rocky planets exist in the habitable zone. Because due to all this complicated things we have discovered, migration, scattering, all these dynamics in the solar, we do not know what is the. We are sure that we have a lot of low-mass planets in planetary system, but what are the characteristics, what is the eccentricity of this object, what is the frequency, we do not know. And it will be extremely difficult to convince politicians or people to pay for extremely expensive experiment to search for life on other planets without having some kind of estimation on the number of this kind of planet. So we would like to prepare some kind of list of targets. Because let's imagine you have huge satellite combination of many interferometers in the space. You cannot measure 1,000 stars to find what are the interesting objects to be measured. So we need to prepare the list of targets in advance. And I believe we have the possibility to do it. And I will finish with this diagram here. What is a dream? I don't know, in one generation or something like this. Is not to send a rocket to see if life exists on one of these interesting targets, but it's only to do some kind of chemical analysis of the atmosphere at some distance. Because if you consider this was done by space measurement of the 3 planets, here you have Mars, Venus, and the Earth, and you have these 3 systems have been formed at the same time with the same mechanism. Then after they have diverged. The atmospheric characteristics of these 3 planets have been completely different with time. And today, as you know, that the atmosphere of Mars and Venus, 96% of carbon dioxide, but a very teeny fraction of carbon dioxide in the Earth's atmosphere, 0.04%. If people are discussing a lot of the influence of carbon dioxide, but it's a very minor component of the Earth's atmosphere. But at the opposite, you have a huge 20% quantity of oxygen in the Earth's atmosphere. And this is completely abnormal, because oxygen loves to do some chemical bonds with rocks to produce oxide. So if you are looking what kind of physical process are able to produce and to accumulate 20% of oxygen in the Earth's atmosphere, people have been able to identify only one single possibility. It's biotic chemistry. Chemistry related to life. It's only because we have life on the Earth that we have been able to accumulate 20% of oxygen. So we can complicate the story with additional molecules and so on. But you see that at distance, at several light years, you have the capability to detect some hints of existence of life just doing chemical analysis. But evidently, you know in advance where to look, to what kind of planets are suitable for that. And then after, you have to succeed to stop the light of the star and to do the spectra of this kind of interesting object. So the path is known, but it's complicated. Thank you. And evidently, I have to thank my collaborators for having contributed to this search of planet, and also to some of colleagues having helped me to provide some of the slides I've been using today.
So Professor Mayor is willing to answer questions, so if anyone would like to ask questions, then please go ahead. Well, I can ask the first question. Okay. And that, so you showed the picture of the estimated number of planets against time, and there was the explosion in 1940. What was the reason for that, and how does that relate to what we know now? I mean, those numbers are much too small, as you know now. Is that right?
In fact, at the beginning of the 20th century, the theory I believe, proposed by Sir James, was the fact that to form the disk or the nebula, to having the capacity to form planet, was a very exceptional event when you have a crossing by another star close to the star. You pick some part of the envelope, form a disk, and this phenomena is completely unexpected because the probability to have so close crossing is very, very low. So if you calculate the probability to have such an event, you have maybe one us, and it's all. So this was the reason why people, at the beginning of the 20th century, believed that it will be extremely hard to have planetary system. And then suddenly, in the 40s, people start to do some spectra, and very good high-resolution spectra of stars, solar-type stars, and discovered that you have a strong drop of the velocity, and the low-mass stars are slowly rotating. So you don't have the same difficulty to form this kind of nebula, and probably a part of the angular momentum is stored in the disk and so on. Okay. So.
Yes, taking you back also to the early days of extrasolar planets, and you talked about the ones many times the mass of Jupiter with an orbital period of only 4 days. And you also talked about migration. Is there evidence that those planets are falling into their respective stars?
So I'm asked to repeat the question. So the question is about the early days of extrasolar planets and the detection of the short period Jupiters, and the question is, are those planets falling into their stars?
Yes, in fact, we have some hints that probably this happened for some of planets, and we can have some unstable orbit for some objects. And I don't remember the name, the denomination, but at least we have one example of a very short object where if you estimate the possibility, the time scale for the planet to be engulfed, it's probably shorter than the time life of the system. So probably we should expect a catastrophe for this system. And we have another observation. It's the fact that for one object, lithium-6 was discovered, and lithium-6 is not supposed to survive the formation of a star. So probably it's only the only possibility to explain this observation is the fact you have after the formation of a star, much later, you have the engulfment of one planet, bringing some lithium-6 in the atmosphere. So I'm completely unable to answer what is the fraction of planet lost by this kind of phenomena, but probably this should exist.
These cases in which the orbital plane of the planet makes a large angle with the spin axis of the star, one can imagine that could arise from chaotic orbital dynamics, but is that a rare case? You quoted one example. Are there many other cases like that?
Yes, it's worse like this. I can try to find a slide. It was maybe slightly too technical, so I drop it. No. Yes, this is a good one. Lecture. What it is?
Lost AP.
Sorry. Voilà. Okay. Amaury Trio did this recently. I believe it's still not published. This is a density of probability based on the existing observation of the angle between the spin axis or equatorial plane of of the star versus the angle of the orbit. And you see that and this, if you have kind of expression due to the interaction with the quasi-mechanistic dynamics, and then taking into account the tidal left friction between the planet and the atmosphere of the star, in fact, you see that you have a crazy agreement between the observation and the theory. So I don't know if it's correct because it's very recent, but in fact, it's not this kind of difficult situation is not rare. It's a relatively frequent situation. It's completely strange because all the first Rosetta measured was quite boring aligned system. And from 1 year, we have a lot of these retrograde and things like this. So I'm not expert because I'm a little bit ashamed because you have people in the room here much better than informed this kind of thing, because here in Cambridge you have people doing this, analyzing this kind of dynamical situation. So, but I believe this is a very stimulating domain because you put the finger on the complexity of the formation of this long period objects.
Any other questions? Oh, okay.
Thanks very much for the talk. It was very interesting. Assuming that we have found a planet which is kind of like Earth-like planet, and we have detected that there is 20% oxygen in its atmosphere, what do you think the next step would be, given that the planet is like a few light years?
So the question is, what's the next step when we detect a planet with 20% oxygen in its atmosphere?
Yes, let's imagine 20, 30 years from now, we have this situation that we have sent some interferometers, detect the ozone 9.7 micron transition of oxygen. And so we will have strong hints that we have life on this kind of object. So this will be first extremely philosophical influence. Life is a product of the normal evolution of the universe. And it's not a unique phenomena. So this is okay. But after what we can do more. So eventually you can try to increase the resolution to detect many kind of molecules. This is one possibility. You can build a specific instrument to do some extremely precise photometry measurements of the planet in different wavelengths. Why? Let's imagine you are looking at the Earth as a function of time. Due to the rotation of the Earth, with existence of continents, the color of the Earth is changing continuously due to clouds, alternance of continents versus ocean, and so on. So you will have the possibility to, I don't know it's easy because you have a lot of photons, but to reconstruct the geometry of the surface of the planet. It's one possible, a typical example you can do. If you had, okay, you have a lot of people have a lot of ideas to build the more complicated missions with to the different kind of measurement. But I believe this is not too long future. I believe this could be done.
A final question? Okay, well, then I'll just say a few words. I mean, I'd like to thank Professor Mayor for giving a really excellent and wide-ranging lecture. He's talked about technological challenges and overcoming them, and he's talked about problems which we as theoreticians in DANTP recognise, and he's also covered some of these enormous questions about the possibility of detecting life beyond Earth and beyond the solar system, and almost what we might do next if we do discover it. So I'd like to thank Professor Mayor again for giving the 4th Andrew Chamblin lecture.
Thank you very much.
Thank you very much.